base b of x. Let's say I want to get this x all by itself. Get out of the mindset of thinking you have to multiply or divide every single time. You are actually going to do something to both sides. And what we're going to do, since exponents and logarithms are inverses of each other, we can use them to cancel each other out. So what we're going to do is we're going to raise these to a base of an exponent. And I'm going to raise it to the base exponent b. So I'm raising this side to an exponential function where I have b to the y. And that's going to equal what I do to one side, I have to do to the other side. So I'm going to raise the other side to an exponential function with a base b. So that's log of b of x. And now why did I do this? Logarithms and exponents are inverses of each other. So what's going to happen is this b raised to the log base b are actually going to cancel each other out. And then x is going to drop down. And so we really have b to the y equals x. So this is the step in between this and this. And we can actually work backwards too if I wanted to. We could work back to this, and we'll see that in just a second. But exponents and logarithms cancel each other out as long as they're the same base. That means they need to be the same number. So once again, if this b was a 5, this would actually be 5, and this would be 5 to the y. Same bases, exponent logarithms cancel each other out. They're inverses of each other. All right, let's see how that works with these problems. First of all four of these are true statements. All four of these are true statements. Log base 3 of 81 does equal 4. But a lot of times with logarithmic functions, we always change them to exponential functions because they're easier to work with. So we're supposed to change the following to be an exponential form and not logarithmic form. So what we're going to do is we're going to recognize that this is base 3. So we're going to have an exponent, base 3, to cancel out this. That's going to look like this. I'll have 3 raised to the log base 3 of 81. But what I do to one side, I have to do the other side. So I'll raise the other side to an exponential with a base of 4. Notice this is still fine because we have that one-to-one property that allows me to do this. These are inverses of each other. So 3 raised to the log base 3 are going to undo each other. And so we're left with just 81 equals 3 to the 4th, which is a true statement. In other words, 3 to the 4th equals that 81. Once again, log base 3 of 81 is saying 3 to the 4th equals 81. That's what log functions are saying. This one should be saying 2 to the negative 2 equals 1/4. But using exponents to rewrite it in this fashion, I'm going to notice that it's base 2. So I'm going to raise both sides to an exponent with base 2. So we'll raise the left-hand side. So I have 2 to the negative 2. Raise the other side to 2 to the log base 2 of 1/4. My 2 raised to a log base 2 are going to cancel out because they're inverses of each other. And then I'm just left with 2 to the negative 2 equals 1/4, which is a true statement. 2 to the negative 2 is 1/4. Once again, you can see that here. Log base 2 of 1/4 is really saying 2 to whatever's on this side equals 1/4. That is what a logarithmic function is saying. All right, so most of the time when you're looking at logarithms, it's easier to think about what it would look like as an exponential function. All right, if I needed to go the other way, I'm supposed to change the following exponential expressions into logarithmic form. I have base 4. that tells me I need to use log base 4 to get rid of this exponent. So logarithms get rid of exponents, and exponents get rid of logarithms. So if I'm starting with an exponent, I need to use a logarithm to get rid of that exponent. And that logarithm needs to be log base 4, because my exponent is base 4 as well. Well, what I do to one side, I have to do the other side. So I have log base 4 of 16. Log base 4 and exponential 4, base 4, are going to cancel each other out. And that 2 is going to drop down, and we'll be left with 2 equals log base 4 of 16. Once again, a logarithmic function is only saying 4 to this power equals 16. So that is a true statement. Let's do the same thing here. I notice my base is 2 of my exponent. To undo exponents, I need to use logarithms of the same base. So that tells me I need to use a log base 2. So we're going to do log base 2 of 2 to the negative 3. That's going to equal log base 2 of the 1 over 8. Log base 2 and the exponent base 2 are going to cancel out. And I'm just left with that negative 3 equals log base 2 of 1/8. Any questions on any one of those four? So that's really what logarithms are. They just undo exponential functions, just like exponential functions undo logarithmic functions. All right, the next part we're going to talk about is how to graph a logarithmic function. And we're going to start off with the fact that I'm going to start with 2 to the x. I'm going to graph 2 to the x, and then I'm going to graph its inverse. The inverse of 2 to the x should be a logarithm, because an exponent's inverse is a logarithm. A logarithm's inverse is an exponential function. So let's first graph this f of x equals 2x. In order to do that, I need to have an x and y. I need to plot 2 points. I'm going to plot one point that makes my exponent 0, which is going to be 0. The next point I'm going to plot will make my exponent 1, which is 1. So that would be 2 to the 0th, which equals 1. Anything to the 0th power is 1. Don't forget that. Even e to the 0th power is 1. E to the 0th power is 1. Now when I plug a 1 and I have 2 to the 1st, anything to the 1st power is itself, so it's 2. So plotting those points, I have 0, 1. I also have 1, 2. I'm not going to write it, but we should know that there's a horizontal asymptote at y equals 0. I am going to write it down here. I'm going to say we have a horizontal asymptote at y equals 0. I'm just not going to draw on the graph because we've got more things to draw on there. So this doohickey right here, that is my y equals 2 to the x. Now I'm supposed to graph its inverse. Let's find its inverse first. Let's find what its inverse is. In order to find an inverse, you switch your x and y values and solve for y. So that's exactly what we're going to do. We're going to find its inverse by switching our x and y values. So instead of being y equals 2 to the x, I'm going to have x equals 2 to the x. I'm sorry, 2 to the y. Make that y a little better. I need to get that y by itself. It's trapped by an exponent. The only way to get an exponent out is to use a logarithm, because logarithms undoes an exponent. And I know what logarithm to use because this is base 2. So I need to use log base 2 on both sides. So we're going to have log base 2 of x is going to equal log base 2 of 2y. Well, guess what? That log base 2 and that 2x of the base exponent are going to cancel each other out. And I'm just going to be left with that y equals log base 2 of x. The only thing I'm going to add to that y is I'm going to add a little -1 to it to let me know that I'm talking about the inverse. So this is my inverse function. This is my regular function. That's my inverse. Well, the easiest way to graph a logarithmic function, knowing that it's inverse, is to take your exponential and flip your xy values. So we're going to take this chart here, rewrite it down here, but this on x and y inverse. Our x and y values are going to switch. So instead of 0, 1, it's going to be 1, 0. So we switch these values. No, that says switch these values. And so instead of 1, 2, we're going to have 2, 1. Okay, so plotting those points, like I said, we have 1, 0, which is here. And I have 2, 1, which is right here. I'm going to tell you right now, my exponential function has that horizontal asymptote. Well, this one's going to have a vertical asymptote. So this one right here is going to have a vertical asymptote at x equals 0. So we're going to have a vertical asymptote at x equals 0. So this graph's going to look something like this. And for those of us that got this right on the test, inverses should just be reflected over y equals x, which it is, which means that horizontal asymptote is going to be reflected too. That's what makes that vertical asymptote. So this is my log base 2 of x. What's important here? Exponential functions have a horizontal asymptote. Logarithmic functions have a vertical asymptote. Neither one has both. So once again, an exponential function has a horizontal asymptote that's at y equals 0 unless it's shifted up or down. So a logarithmic function with its vertical asymptote is going to have it at x equals 0 unless your graph gets shifted left or right. Bless you. Why'd you plug your nose, though? That's like the whole point of the sneeze. Your eyes are going to pop out. Isn't that like an urban legend? Like if you...
But doesn't that like make sense, though?
No, because they also say that you sneeze at the same force of a hurricane.
Oh, I thought a sneeze just was like really fast.
Okay, we're going to use what we did on the last one to graph all logarithmic functions. There's multiple ways to graph logarithmic functions, but this is one of the easiest, and we'll talk about how. So since all logarithmic functions are inverses of exponential graphs, and since it's easy to graph an exponential graph and not so easy to graph a logarithmic function, we are actually going to take the inverse of a log, graph our exponent, flip our xy values, which will get me back to my logarithmic values. So I'll say that once again. We start with a log. Let's see this first example. I have log base 3 of x. It is really hard to pick x values that plot nicely on here. All right, it can be really hard to pick values for these that actually work out nicely on these. So instead of graphing this, I'm going to take its inverse. Its inverse is going to be an exponential function. I'm going to find 2 easy exponential points to graph. And then all I'm going to do is I'm going to switch my x and y values to get me back to my logarithmic function. If that sounds confusing, let's do an example here. So I have y equals log base 3 of x. Rather than going right to plotting an xy table, I am going to find its inverse first. So I'm going to find its inverse. To find its inverse, I switch my x and y values to give me x equals log base 3 of x. If I have log base 3, to get rid of log base 3, I rewrite it as an exponential function with a base 3. Yes?
X equals log base 3 of y.
Oh, yeah, sorry. Yeah, I should have a y. I kind of switched them both and left them both x's. Yeah, perfect. But we do need to get that y by itself, so that's why I raise it to that exponent with base 3, which means I have to do the same thing to this side. Well, log base 3 and then exponential base 3 are going to cancel out. And I'm going to be left with, I'm going to change it to y inverse equals 3 to the x, because this really is the inverse. I'm still graphing this, but I'm using its inverse to find those points. So now I have y inverse equals 3 to the x. So what I'm going to do is I'm going to come over here. Y inverse equals 3 to the x. I'm going to come up with an xy table to find two easy points. So we'll have an x and a y inverse. Well, two easy points to plot would be 0 and 1, because 3 to the 0th power is just 1. 3 to the first power is going to be 3. So if I was going to graph this, I would have an easy time. I just plot those 2 points. I really don't care about graphing this. I want to graph my original equation. We're just using this table to come up with points for my original equation. So we are going to take these and switch them so that I can find my y equals log base 3 of x. So that table is going to be x, y. I switch my x and y values. So instead of 0, 1, I'm going to have 1, 0. Instead of 1, 3, I'm going to have 3, 1. Now I can plot those 2 points. So I'll plot 1, 0. I'll plot 3, 1. 1, 2, 3, 1. I'm going to remember that logarithmic functions have a vertical asymptote at x equals 0, unless we have it shifted left or right. And so our graph's going to look something like that. That right there is my log base 3 of x. Once again, because this can be a little confusing. Logarithmic functions are hard to put a value in without thinking about their exponent inverse or rewriting it as an exponential function. So that's exactly what we do. We do the inverse to figure out what my exponential values would be, flip your x, y's, and you can bring it back to your logarithmic function. Now we're supposed to do domain, range, and horizontal or vertical asymptote. Our domain, with exponential functions, your domain is always negative infinity to positive infinity. With logarithmic functions, it's going to switch. It's going to be 0 to infinity. And that's because we are switching our domain and ranges. All domains of exponentials are negative infinity to infinity. For logarithmic functions, it's going to be vertical asymptote to either infinity or negative infinity to there. Our range, however, for logarithmic functions are always going to be negative infinity to infinity. So exponential, domain, negative infinity to infinity. Range of logarithm is negative infinity to infinity because those two values switch. Our domain and ranges switch. Finally, we don't have a horizontal asymptote. We have a vertical asymptote at x equals 0. X equals a number means it's vertical. All right, our next one. We are going to go ahead and we're going to find the inverse, but instead of finding the inverse of y equals log base 4 of x minus 2, we are going to find the inverse of just y equals log base 4 of x. We're just going to find the inverse of the parent function. You can find the inverse of the whole thing, and it'll work out just fine. It's just sometimes when you get too complicated, it's hard to find inverses. So I'm just going to find the inverse of the parent function. And once I get my endpoints, I'm going to make sure to go down 2. So I'll use this to get my points, plot them, and then just go down 2. All right, so the inverse of y equals log base 4 of x. We switch out our x and y values, so we're going to have x equals log base 4 of y. Well, I would take an exponent of 4 base on both sides, so my log base 4 and my 4 will cancel out. And I'll just be left with my y inverse equals 4 to the x. Plotting 2 points for this. I would plug in 0 and 1, because 4 to the 0th power is 1, and 4 to the first power is 4. Then we're going to take those values and switch them. Because this was the inverse, right? This is my inverse. And so I'm going to switch them so I can get back to my original equation. So I switch my x and y values to 1, 0, 4, 0. This will give me my original log base 4 of x. That should be a 4, 1. So we're going to plot these 2 points, and then we're going to bring them down 2. So I'll plot those 2 points. We have 1, 0, and we have 4, 1. And then we have to drop them down 2 because it was log base 4 of x minus 2. So we'll drop those down 2. Drop these down 2. My horizontal asymptote is still in place because I didn't shift left or right. So we're going to have a graph that looks like that, where the domain would be from negative infinity. Not negative infinity, it'd be from 0 to infinity. I was thinking about the range because we do have a vertical asymptote at x equals 0. My range is the one that will be from negative infinity to infinity. And finally, I have a vertical asymptote at x equals 0. Once again, plugging numbers into a logarithmic function can be difficult. So I use my exponential, knowing I can convert it to an exponential function. And knowing that it's inverse, I just got to find those values and flip them. Any questions on any one of those steps? Remember, I talk a lot while I'm doing this, so you shouldn't just write down what's here. You have to have something that's written down that you're going to be able to study later on, correct? So make sure you have enough notes in there that you understand why I did what I did. All right, last thing that we really need to talk about is common logs. First of all, if you look at your calculator on the left-hand side, if you have Texas Instrument one, on the left-hand side, by your kind of x squared button, maybe a little lower, you do have a log button and an ln button. Common log is the only button you have in your calculator. We'll talk about changing bases in just a second. So anytime you press that log button on your calculator, you are typing in log of some number. There is no base written here. If there's no base written here, it is always known that the base is actually 10. So if I ever write log of a number, you automatically know that it's base 10. You need to know that because that's the mode your calculator's in. Whenever you press that log button, it is log base 10. So if I give you log base 3 of 4, you can't enter that in your calculator right now, all right? Because you only have a log base 10 button. You also have an ln button. ln of x is known as the natural log. That is actually log base e. So the only two that you can actually plug in your calculator are log base 10 and log base e of a number. That's all you can use your calculator for right now. So once again, you could not type in log base 5 in your calculator right now. We'll talk about changing base, I believe, on Monday. But as it stands, you can only do log base 10 and log base c. Know these. Know these, because I don't want on a test, I write log base 4 or something, and you're just like, what base is this? Because I won't answer. I won't answer on either one of these if you ask for the base. You just need to know them. All right, let's do these last 4 examples, and then we're done. Log base 5 of x equals 3. I need to get that x by itself, which means I need to get rid of this log base 5. To undo a logarithm, I have to use an exponent. So what we're going to do is we're going to take a base 5 exponent to both sides. So I have 5 to the log base 5 of x is going to equal, well, what I do to one side, I have to do the other. So I have 5 to 3. Remember, this is equivalent because it's 1 to 1. These two things are still equal. Well, the good thing is here, an exponent of 5 cancels out a log base 5. Remember, we are not multiplying. This is not a multiplication. This is raising it to an exponent with base 5. I am not multiplying, but these undo. And what I mean by multiplying is sometimes on tests I see this. 5 times log base 5 of x equals 5 times 3 or something. These do not cancel out. You cannot do this. That's not true. 5 times log base 5 does not undo itself. It has to be 5 raised to the log base 5. All right, but then my x will just drop down, and I'll have 5 cubed. Well, 5 cubed just equals 125. And so that's my answer. Once again, it's much easier to go through exponents to solve these. It's much easier to go through exponents to solve them. That's why when we're graphing, we go through exponents to graph it. All right, next one. We have log base 4 equals 1/2. Well, I see it's log base 4. The only way to get rid of a log base 4 is to take, erase it to an exponent of base 4. So I have 4 to the log base 4 of x, which means I have to do the same thing here. 4 to the 1/2. Log base 4 and exponent 4 are going to cancel out. And we're just left with x equals 4 to the 1/2. Well, 4 to the 1/2 is really just 2 square root of 4. This 2 tells me what to square it as. This 1 is actually here. So just to recap, that 1 would go there, this 2 would go here, and that would work with all fractions. Well, that's just the square root of 4, which is just going to equal 2. Not plus and minus 2, it is just 2. The only time you do plus and minus is if you're taking the square, if you are the one taking the square root of both sides. The square root was provided to me, so I'm not plus or minus. All right, 2 more. Same type of deal here. I need to get rid of this log base 5, so I notice it's base 5. So I'm going to have a base 5 for my exponent. So I'll have base 5 exponent, log base 5 of 125. So 5 raised to the log base 5 of 125. Do the same thing on the other side, 5 raised to the x. My log base 5 and my exponent base 5 are going to cancel out. I'll be left with 125 equals 5 to the x. Well, the only thing that works there is x equals 3, because 5 cubed equals 125, so x is going to equal 3. Last one's actually the one-to-one property. Just like with exponents, if I have log base 8 of 32 equals log base 8 of 4x, that must mean that 32 equals 4x. But algebraically proving that, to get rid of log base 8, I would need to raise this to a power with base 8. So I'd have 8 raised to the log base 8 of 32 equals, do the same thing to the other side, 8 raised to the log base 8 of 4x. Log base 8 and base 8 will cancel out. Same thing on the other side, base 8 and log base 8 will cancel out. I'll be left with 32 equals 4x. X equals 8. Yes?
Do we have to like show that work, or do you think like, or can we just like realize that it's 1 to 1 and just say 32 equals 4?
You can absolutely realize it's 1 to 1. In fact, that's going to be one of our properties later on. I'll just
Okay.
say it. Yep. But it's nice to know the logic behind it in case you forget it.
Yeah.
Sometimes you just get in solving mode and being able to cancel out. You're just like, oh, it's 1 to 1, but I got the answer either way. Any questions on that? Okay, then